our next step in our study of the accelerated motion, we're going to go back to Tim's PowerPoint notes, and I would ask you to now reach his notes. It is the first handout I gave you about motion. Please pause your video for a little bit and then come back once you have the notes and you're on the right slide. So now let's cover Tim's notes in here. He's going to talk now about the instantaneous and average values for velocity, speed, and acceleration. So consider a car whose position is changing and a patrol officer checking the speed with a radar gun. The radar gun is going to measure the position of the car during successive snapshots, and those are going to be shown in yellow in here. And we can see here each one of these yellow lines that I am now making a little red ink mark represents the position of the car when the radar gun, okay, showed here, took a snapshot of the position of the car. Is this car speeding up, slowing down, or moving at a constant velocity? And moving forward, the car is speeding up. And we can say that the car is speeding up because the distance between consecutive readings, the distance between the consecutive yellow lines, is ever increasing. Of course, that this means that we are making the assumption that the time between consecutive snapshots stays always the same. Okay? Well, moving forward in here, we can label each of these positions with an X. So X1 for first position, X2 for second position, X3 for third position, and so on. And the interval between them is going to be delta t. Okay, and that time is always the same. Okay, we're assuming this. Then the car is going to have an average velocity, VA, VB, and VC inside of these intervals. And VA is X2 minus X1 over time. VB is going to be X3 minus X2 over time. And VC is going to be X4 minus X3 over time. So these are just displacement over time for the velocity. Now he's going to want us to focus on this displacement from X2 to X3. Notice that the speed changes from X2 to X3. So VB is actually the average velocity for this interval, not the instantaneous velocity, not the constant velocity. Okay? But if we increase the sample rate of the radar gun, which basically means making the time interval becoming a little bit smaller, you guys can see now that the time is running a bit faster. The velocity, the average velocity on this interval is closer to the actual velocity of the car. And if we make this, if we increase even further the sample rate of my radar gun, that average velocity is going to get closer and closer to the instantaneous velocity, until a point where if this interval here is almost zero, the velocity of the car does not really change that much on that interval, and then we're going to call that the velocity, instantaneous velocity of the car on that point. So this is what matters for us. We are not going to deal with calculus in this class, and basically that's what we need. So same thing when we're trying to find acceleration, okay? If I just make the time interval be very small, the average acceleration will be based the same thing as instantaneous acceleration, and that is all of what we need. The next set of equations are actually Tim's derivation of the equations of motion. Okay, S equals ut plus 1/2 of at squared, V equals u plus at, V squared equals u squared plus 2as, and S equals u plus v times t over 2. And I'm going to leave this with you guys to read these derivations. We have already derived those equations in class using my set of notes and based on graphs. Okay, so